Thanks. Yeah, ignoring things that have nothing whatsoever to do with religion, because I know you're an atheist, as indeed am I. Is there anything left? No, we know there's no afterlife, you know, all of that stuff. Is there anything left of religion that is remotely scientifically valid to believe in? And I hope you're going to say no.
Well, it's always a little bit of an unfair comparison, right? I mean, religion was not invented as a precursor to science. Religion was always something both richer and less rigorous than science was. So religion has aspects of attempting to account for the universe, attempting to explain it. And I would say that as far as that purpose or goal or task of religion goes, no, you would always pick the scientific explanation when it came into conflict with some religious ontology, for example. But there's a whole bunch of aims that religion has that science doesn't care about, like how to be a good person, you know, how to live in society, how to have a sense of community, things like that. I think that as open-minded people, you know, we should recognize that for thousands of years, the best, most serious, most careful thought about what it means to be a good person was carried out within religious traditions. Some of that thought ended up with complete nonsense, but some of it might have been good. So I think that we should treat religious wisdom traditions just as we would treat pagan or atheist religious wisdom traditions. Is there anything good there? Maybe there is, maybe there's not. You know, I kind of like the Sermon on the Mount. I've heard worse pieces of advice than that.
Over here.
Thank you, that was a wonderful lecture. Going back to that massively long equation, the
yes.
W equals whatever.
That's the crowd pleaser, yes.
You mentioned there was a label for gravity in it. Yeah, that's
yes,
it.
That's right.
But you said it was a quantum mechanical equation.
I did.
But quantum mechanics doesn't explain gravity, so I was just wondering what all that was about.
See, this is what happens when you go to lectures by people other than me. They tell you bad things. So the truth, carefully said, is that we do not have a complete theory of quantum gravity. We don't know what happens in a black hole, at the Big Bang, and so forth. What they don't tell you, but is equally important, is that we have a pretty good theory of quantum gravity that works in our everyday lives. If you want to use the principles of quantum mechanics to calculate the motion of the Earth around the sun, we can do that. No problem. So putting gravity in here in the core theory, as long as you keep in mind that you're talking about a very restricted regime of possible configurations of stuff, is perfectly okay.
Up the back here.
Hi, you had the picture of the early universe as being uniform and smooth.
Yes.
If it started off as uniform and smooth, where did the asymmetries and the clumpiness come from?
Good. Uniform, smooth, and very, very high density. The universe was when it started. When it ends, it will be uniform, smooth, and very, very low density. That's a very crucial difference. Because when you tend to think, like the cup of coffee example, right? You tend to think that when things are separate and inhomogeneous, that is low entropy, and then when they're all mixed up and smooth, that is high entropy. That's only true because the systems that we're used to dealing with in our everyday experimental lives have very low mutual gravity, okay? The gravitational force of the cream on the coffee is completely irrelevant. It's feeling the gravitational force of the Earth, but there's no important gravitational force between the cream and the coffee molecules. In that case, it is usually true that separate means low entropy, mixed together means high entropy. The example of oil and water should convince you that's not always true, but that's another lecture. In the early universe, when the density was extremely high, the gravitational forces between different parts of matter were extremely, extremely important. In that case, when you're very, very dense, high entropy means lumpy. High entropy means wildly fluctuating and inhomogeneous. You want to sort of crumple into black holes in empty space. You don't want to be smoothly arranged, which you can see because this smooth arrangement very quickly changes into something else. So where the structure comes from, it was always there. It was never perfectly smooth, right? It was very, very, very smooth, more than 1 part in 100,000, certainly. But it was very low entropy, which means it was in a very specific orderly arrangement. And as the universe sort of expanded and cooled and relaxed, that gravitational force, if there was a slight overdensity in one region, it increased the overdensity. If it was underdense in another region, it increased the underdensity. Gravity increases the contrast knob on the universe for a while. And today, now that we're starting to accelerate, it will go away again.
Up the top.
Yeah, brilliant lecture. Thank you very much indeed. I can understand when you say that we're all going to die. I can understand the concept that by the heat death of the universe, obviously nothing, including any mechanical thing, because of the energy and what have you. But if we're not religiously created or connected to God as beings, we are immensely complicated. But why long term is there no a reason that not necessarily life, that your brain could be replaced by a machine, as parts of your body could be, consciousness is a developmental thing, who says you can't have that at some stage in the future? I can't see, putting to you, a scientific reason why that necessarily means that we won't be able to overcome death as we understand it at the moment for at least some time.
No, actually, I think that you're making a very good point, and I just agree with everything that you say. When I said you will die, I'm thinking like a physicist. So in the next 10 to the 100 years, you will die. Not necessarily in the next 100 years. The plot I showed you, the biological plot, says that there is sort of a natural lifespan for human beings, and there's even sort of a natural upper limit, 115, 120 years. Even if you're perfectly healthy, you will die after that. There is no law of physics that says we cannot reverse age ourselves. Just like you can clean up your room and chill a bottle of champagne, you can lower the entropy inside your body. There are things that build up, telomeres get damaged, and there's a whole set of things that happen during the aging process that right now biology is clueless to undo, but there's no obstacle in principle. We can do it for a cell that was a stem cell and sort of matured into a regular functioning cell. There are people who can reverse age them back into stem cells again. And once you're there, from a physicist's point of view, now it's just technology, right? Now it's just like, think about it hard. When I talk to my most optimistic friends, they say that I will die someday, soon. But if I were to have, grandkids, they're not so sure.
You said that particles we haven't found by now are insignificant for reasons. But what if two insignificant particles that you smash together produce something very significant? How would we know that that's not the case?
So yeah, of course, significance is in the eye of the beholder. If you're a professional physicist, it's very significant. But for the functioning of you and me, it will not be significant. The point is that not only does the existence of the diagram on the left imply the existence of the diagram on the right, but the numbers are also the same. So on the left, the number that you're talking about is how strong does the new particle interact with the existing particles? How much of an influence could it possibly have? On the right, the number you're talking about is how frequently would you make it if you were to collide ordinary particles together? So the answer is that if this new particle interacted strongly enough with existing particles that it could possibly influence us in any noticeable way, you would be making it by the bucket load at particle accelerators. You would have not just made one, you would have made many, many, many billions of them. They're not there.
Do we have any more questions from the balcony? Up here?
Hi, thank you. As what you were saying about the different ways of explaining the universe through macroscopic and microscopic, does that mean that you don't believe in a theory of everything then, or?
Oh, good. Yeah, theory of everything was a phrase that almost started as a joke, and people took it a little too seriously. What that means is, down here at the microscopic level, we know that we're not done, even just at the microscopic level. We know that we don't know what the dark matter is. We don't know what the dark energy is. We don't know what the rules of quantum gravity are in regimes like black holes and the Big Bang. So we're not done. even if we were done at that microscopic level, we wouldn't suddenly have solved biology or economics, right? These emergent higher level laws are in some sense implied by the microscopic laws, but it is completely infeasible to actually derive them in any direct way. It's much easier just to go out and do experiments in biology. So the phrase theory of everything, as physicists use it, refers to a hypothetical microscopic theory of all the particles and forces in nature. So gravity, the strong and weak nuclear forces, and any particles and forces we haven't yet discovered. But it was never meant to imply anything beyond that in the macroscopic world. So in that narrow, restricted technical sense of theory of everything, it's completely possible that we will find one. We might even find one soon. Who knows? It's impossible to predict. In a broader sense of knowing all the possible emergent vocabularies to correctly describe the world, I don't know whether you could imagine ever getting all of the possible emergent descriptions. I haven't really thought about that. I would not be surprised if that were just not possible. On the other hand, in a finite universe, maybe there are only a finite number of them, and you could imagine doing it. But that's not what's generally meant by a theory of everything.
Over here.
Hi. So you said that we're made out of up and down quarks and electrons.
Yes.
What about all the other particles, the strange quark and all these sorts of things? What would happen if we didn't have those? What do they do?
Well, that's a very good question. You know, I'll give an answer sort of in the context of what you just heard. You know that entropy likes to increase. If you have one particle like a top quark, let's say, that can decay into a set of many particles. And that many particle system has a higher entropy than the top quark does. So these are the lightest particles that can't decay. Every single particle you see here has a reason why it can't decay for some reason or another. Charge conservation, momentum conservation, or whatever. So all the heavier particles, if you make them, they just decay into these. The closest to a counterexample is the muon. The muon is the is the lightest particle not in this list. It lasts for a millisecond, a microsecond, 10 to the minus 6 seconds. Just not going to do very much. So they're there, we can make them. We discovered the muon a long time ago. The muon was discovered by Carl Anderson at Caltech across the street from my office, from cosmic rays coming down, but they go away very, very quickly. So they're interesting, they're there, they're not part of our biology.
Did you see one that you seem to be pointing to somebody?
Well, there's one just right there, right
Yep.
in the front row, yeah.
Okay, so yeah, it was great. My question is, like you mentioned, no, it was really good, really good. The parts that I understood. No, but just kidding. You mentioned about entropy and the fact that complexity allows you to control entropy. You can go back, you can go forward. And then we mentioned one of the persons here asked about how, you know, if we develop this complexity even further, our intelligence even further, and allows us to control entropy more and more,
Yeah.
can we control it? And I think I'm talking billions of years. Can you actually control it to a point that entropy could stop or reverse? And if we do, what does it say about patterns of the universe?
No. You can't. No, you can't. The control, so you can build a refrigerator. You can clean your room. You can do things, as you say, your cells can repair themselves. There are things that we can do in the environment we find ourselves in that lower the entropy of subsystems of the universe. But generally, it's not necessarily a law, but it's a very good rule of thumb. When you do that, not only do you increase the overall entropy of the universe, but you increase it faster than you would have by just leaving things alone. So there is a limit. We think that there's a maximum entropy we can reach. So you can try to sort of keep yourself maintained and thinking and conscious. And by the way, like, there have been people who've talked about things that could last forever, but what you and I think of as life or consciousness are not included in that category because we really rely on entropy increasing. The fact that you can remember the past and not the future relies on entropy increasing. So someday we will hit the maximum entropy of the universe, and then there will be no arrow of time. There will be no distinction between past and future. There will be no sense in which I'm making choices. about the future. It'll all just be smooth, featureless muck. Every particle will be literally quadrillions or googles of light years away from every other particle, and nothing interesting will happen. And that is inevitable, according to our best current understanding. Sorry.
Over here.
Do you think that us or our descendants are guaranteed to figure out the missing parts of our understanding of the universe, or is there a glass ceiling that we cannot break? For example, are we guaranteed to figure out what happens within black hole singularities, quantum gravity, and so forth? Or will we just never figure those things out?
Yeah, we're not guaranteed anything. We ain't guaranteed nothing. I'm optimistic. If you want me to place bets, I think we will figure out those things. You know, we don't know what happens inside a black hole or at the Big Bang, but we can piece things together, what is plausible, what is not plausible. We get better and better at it. I think we're learning about those things. But the whole process of science is one of hoping that we're able to get better and better at understanding things. You can't predict the rate at which your understanding will go up, or even that it will go up in the questions you want to know the answer to. This is not exactly what you're asking, but there's other questions that might not even have an answer, right? Why does the universe exist? Remember, the idea of an explanation or a reason why is an emergent higher level phenomenon. It might not apply to the universe. The answer for why the universe exists might just be, well, the universe is the kind of thing that happens from time to time. It just is. There's just no better reason than that. And we might not, or there is a reason and we'll never know. That's absolutely possible. So the most important property that the scientific investigator needs to have is not placing demands on what the universe is going to give him or her.
Thanks.
Is there anybody else up on the balcony that would like to ask a question?
So, as I'm sure you're aware, it seems sort of bleak that the universe starts, it goes all these great things, and then it just evens out into cosmic butter. But what do you think? What do you think about? You hear these other physicists, theoretical physicists, discussing alternate descriptions, like what happens before the Big Bang, what happens after everything smooths out into butter. I just wanted to know what you thought about, because I'm sure you're well aware of what they're talking about.
Yeah, absolutely. So, of course, this is an area where the state of the art is extremely speculative. We don't know answers. When I draw pictures like this, every word counts. And the word observable in the title here is very, very important. This is the universe we see. This is not the whole universe. Could there be parts of the universe too far away that we haven't yet seen? Absolutely. That seems very easy. Could it be possible that conditions very far away are utterly different than conditions here? Yes, that is also very possible. Is it possible there was a moment before the Big Bang, or even an infinity of moments before the Big Bang? Yeah, absolutely. Is it possible there were not any moments before the Big Bang and the Big Bang was the beginning? Yes, all these are very, very possible. I'm hoping to make progress. It sounds kind of hopeless when you put it that way. There's so many things we don't know the answer to. But remember, 100 years ago, we didn't know the universe was expanding. We didn't know there were other galaxies. We thought our galaxy was the whole universe. Within the course of 100 years, we've learned an enormous amount about the universe. And so I have every reason to think that in the next 100 years, we'll learn a lot more. But I can't tell you what it is going to be that we're going to learn.
Down here.
Good evening and thanks. I just wanted to ask, for you personally, what do you think will be the next big discovery that you're most looking forward to or most excited about?
Right. Yeah, I used to have a great answer to that, which was the Higgs boson, and then we found that. And then I had gravitational waves, and we found those. So now I don't know. There's nothing on the docket that is, there's many things we hope for and are looking for. The most obvious one is let's directly detect the dark matter, okay? We think that there's 5 times as much dark matter by mass in the universe as ordinary matter. We don't think the dark matter is in this equation. We think that this does not include the dark matter, the core theory right now. So there's something new that we haven't found yet. It interacts with us very, very weakly. We've been looking for it. This is your job. It's Pat's day job, looking for the dark matter. Haven't found it yet. It's completely plausible that in the next 5 years we will find it. But it's possible that we won't. I think that's a good thing to anticipate as the next big discovery in fundamental physics. Of course, the Large Hadron Collider is also running, It found the Higgs boson. It hasn't found anything else yet, but it could find other things. So my prediction is going to sound wimpy, but my prediction is that the next big discovery is going to be a true surprise. It's not going to be something that we were anticipating for decades, like the Higgs was or gravitational waves were.
Gentleman up here in the white. And we'll take 2 more questions after this.
I was wondering what your opinion is of Max Tegmark's idea about base reality being mathematics.
Right, so Max Tegmark, a friend of mine who's a professor at MIT, he has a book too. You don't want to buy that one, you want to get this one. But it's a very good book. There's equations in it, but it's very readable, and it's about the mathematical universe. It's about the idea that at heart, not only is the universe mathematical and described by mathematics, but every single kind of mathematical structure becomes real in some sense. I don't buy it, to be honest. I don't think it's right because our universe seems so specific. Like if literally every possible kind of mathematical universe existed, you would think that in some sense we would find ourselves in a more or less typical universe. And our universe doesn't seem typical in the space of all mathematical structures at all, to the extent that that idea even makes sense. So for the most part, I'm totally in favor of speculations about the multiverse and many worlds and things like that, but only when we are driven to it by this trying to solve some problem. We're driven to the multiverse by trying to solve the smoothness problem of our early universe that we observe. We're driven to the many worlds of quantum mechanics by trying to understand the quantum measurement problem. I'm not driven by any feature of our current universe to propose that all mathematical structures are part of reality. So if I am, then I'll change my mind.
Okay, last chance from up on the balcony.
Can you explain the purpose of neutrinos and can we measure their movement? And could they be used as a new kind of non-radiating X-ray for the future?
Yes. This is a very good question. So the poor neutrino here is the particle I talked about the least. It has this interesting story, I don't know if you know, but neutrons decay. Like a neutron all by itself out there in the world, not stuck to protons, doesn't last for very long. It lasts for a few minutes. It turns into a proton, an anti-electron, and who knows? They saw neutrons decay. It was called beta decay for historical reasons. So they saw the neutron, they saw the proton and the electron, sorry, proton, yeah, and the electron that it spit out. And they measured the momentum of the proton and electron that the neutron decayed into. And remember, momentum is conserved, but it didn't seem to be. The total momentum of the proton and the electron didn't add up to the momentum of the neutron. So Wolfgang Pauli, a famous German physicist, proposed there was a new invisible particle that was emitted with just enough momentum to make up the excess. And he was very embarrassed about this because he had proposed a particle that you couldn't observe. Fortunately, these days we're much better at it. So these days we make neutrinos by the bushel, we detect them, there's no problem. We can actually, because they interact so weakly, there's a fun kind of experiment you can do with neutrinos, which is you can shoot them through the Earth. You can create the neutrinos in Chicago, for example, and you can point them through the Earth and detect them in a detector in a completely different part of the world. Most of them will go right through, but you detect enough of them that it's interesting. Will they therefore be useful as something like X-rays? Probably not, because for the same reason it's hard to detect them, unlike an X-ray which is stopped by bone, neutrinos aren't really stopped by much of anything. They just keep going through. So I don't know, you might have a different opinion about this, but...
Well, there are some ideas about using them for communication, maybe not for X-rays.
Right, that's good, that's a fair point. So because they can go through things, and because they're an alternative, it's harder to like eavesdrop on a neutrino. You can imagine communicating with somebody. It seems to be not a very efficient, energetically way of doing things, but when things exist and are easy to make, like neutrinos, we will invent technological uses for them someday. That's almost inevitable.
And maybe when we have reason to communicate with people in other star systems, for example.
That's true. Neutrinos might be the way.
Okay, so Sean's going to be outside signing books and taking further questions. And thank you, everybody, for your attention, and let's thank him again.
Thank you.